afternoon, and thanks for joining us for our session today. Welcome to day one of reInvent. Today we're going to be talking about how to run large-scale graphics workloads on AWS, and we've got our two customers here joining us today to deep dive on their specific use cases. My name is Samantha Pham. I'm a Principal Product Manager at AWS, and here with me today we have Eli Semery, a tech lead at Snap, and Brian Lung, a Senior Manager of Engineering at Mircom. So just a quick rundown of what we're going to be chatting about today. First, I'm going to give a quick overview of our Amazon EC2 instances and our Amazon managed services that are built for graphics use cases. Then we're going to talk about typical industries and use cases that we see from our graphics customers. I'll run through a few of our customer references before handing it off to Eli and Brian to talk about their specific use cases and how they use AWS. So first, I just want to start by stating that EC2 offers the broadest portfolio of compute instances in the cloud. We have over 500 generally available instances to give customers the best price performance for their various workloads. With these over 500 instances, customers can find the best fit to optimize costs for their workloads. We offer a range of 3 different processor types within our instances. We have processors from Intel, AMD, and our very own built Graviton processors. These Graviton processors can deliver up to 40% better price performance over comparable x86-based instances for various workloads. Additionally, we offer a broad range of hardware accelerators on our instances. So we have things from GPUs from NVIDIA and AMD to media accelerator cards from AMD Xilinx to our own Inferentia and Trainium chips, which were purpose-built for ML inference and training workloads. Today, we're going to be focusing on the instances in the 3 boxes to the right of this scale here, as those are the ones that are built for graphics workloads. So keeping in the spirit of making sure that we offer our customers the broadest set of compute instances for their workloads, we've built many options for our graphics customers. The first one that we have are the G4dn instances. They're our lowest cost GPU-based instance for graphics workloads. They feature AMD Radeon V520 Pro GPUs, which come with 8 gigabytes of GPU memory and start as low as 38 cents per hour on demand. For customers that are looking to access NVIDIA GPUs so that they can access things like CUDA or other NVIDIA libraries, our G5 instances offer the absolute highest performance for graphics workloads. They feature NVIDIA A10G GPUs with 24 gigabytes of GPU memory for rendering large scenes and simulations. Our G4dn instances are great for customers that have less graphically intensive workloads, as they have a lighter weight NVIDIA GPU, which are the T4 GPUs, and those come with 16 gigabytes of GPU memory. And then lastly, within our NVIDIA GPU-based instances, we have the G5G instances. These were the very first GPU-based instance in any major cloud that came paired with ARM processors. They feature NVIDIA T4G GPUs, and they're paired with Graviton 2 processors. We launched these G5G GPU-based instances because we wanted our GPU customers to be able to take advantage of our relentless effort to develop our own processors, the Graviton processors, that push the envelope on price and performance. With the G5G instances, customers can not only lower costs for their existing workloads running on GPU instances like G4dn, but they can also start running cost-efficient Android game streaming applications on a single instance without any emulators. And lastly, we have our VT1 instances. These are purpose-built for live, low-latency transcoding workloads with user-generated content. They feature AMD Xilinx Alveo U30 media accelerators, which can support up to 16 concurrent streams of 1080p content at 30 frames per second. In addition to our broad portfolio of EC2 instances that are optimized for graphics workloads, we also offer a wide range of other Amazon-built services to help support graphics customers. Firstly, we have NiceDCV, which is a high-performance remote display protocol that provides customers with a secure way to deliver remote desktops and application streaming to their end users. We also offer many fully managed services for industries from end-user computing to gaming to media and entertainment. Across these verticals, we offer fully managed services which allow customers to stream applications, provision desktops, deploy and scale dedicated game servers, managed hybrid and cloud-based render farms, and broadcast high-quality streams for delivery to TVs and internet-connected devices. Using our EC2 instances and our managed services, customers across a diverse set of industries from gaming to retail to healthcare and life sciences are building graphics applications to define new categories of products and experiences for their end users. Customers are using real-time 3D graphics applications to deliver immersive experiences for delving into game streaming applications, 3D simulations, to create digital overlays on top of the real world for augmented reality, and to create virtual reality experiences for their end users. These real-time 3D applications are being used to transform productivity, education, collaboration, and retail through virtual trainings, design reviews, and virtual 3D product models for shopping. Across the industries we just talked about, we see 4 main graphics use cases: remote workstations, game or pixel streaming, rendering, and video transcoding. Customers in gaming, architecture, engineering, construction, media and entertainment, and energy are using remote workstations for graphics-intensive workloads like game development, creating animation and visual effects, editing live-action video, creating and editing CAD models, and visualizing 3D seismic data. Tying it back to our EC2 instances, many of our workstations customers are leveraging our G4AD and our G4dn instances to run low-cost workstations in the cloud. Gaming and retail customers are doing game or pixel streaming to stream premium games, 3D content, or live virtual events to any device at any location. Similar to our workstation customers, we see many gaming customers that use G4AD and G4dn instances for these workloads as they provide the right GPU power they need while keeping cost per stream as low as possible. For the rendering customers, we see many use cases within gaming, media and entertainment, healthcare and life sciences, and the industrial industries. They're rendering photorealistic 2D and 3D images for video games, television shows, movies, molecular visualization, and to create digital twins of factories and products for their end users. For these customers, the G5 instances offer the best performance, and with 24 gigabytes of GPU memory, customers are able to render larger and more complex scenes and simulations. Customers in media and entertainment are also doing video transcoding for live broadcasting and to make their created content available on multiple devices to play back from televisions, tablets, mobile phones, and these customers often find that the VT1 instances provide them the best price performance. We also recognize that we're in the very early days of the metaverse, and there are many companies building their vision of what a future metaverse could look like. AWS is providing the tools and enabling the underlying technologies that these customers need to build their vision of what the metaverse will be. We already have customers that are using our EC2 G5 instances to create and deploy those compelling metaverse experiences for their end users. So before I hand it off to our two customers to deep dive into their use cases on AWS, I want to go through a few of our other customer references just to give you a sense of the broad set of use cases that we are supporting currently. So first, we have Ubitus. Ubitus is an innovative company leading the way in building cloud gaming technology. They use our G4AD instances for game streaming. And with those G4AD instances, they're able to optimize their costs by fitting up to 50% more concurrent streams per instance. Secondly, we have Varjo. Varjo is an industry-leading provider of professional-grade solutions for virtual reality and mixed reality. The G5 instances have enabled them to move their high-fidelity workloads to the cloud compared to running on hefty local PCs, because with the G5 instances, they were able to see 3 times better performance compared to our previous generation GPU instances, the G4dns. And lastly, we have TheoLive. TheoLive is the first HTTP-based real-time video streaming service that makes it easy to reach audiences of any size with sub-second latency, powering high-quality use cases such as live sports and virtual events. With the VT1 instances, they can deliver real-time streaming to viewers worldwide at up to 30% less costs compared to comparable GPU-based instances, and up to 60% less cost compared to CPU-based instances without sacrificing on any of the quality that they offer. So now that I've talked through all that, I want to hand it over to Eli Semery from Snap to talk about how they build 3D Bitmojis with AWS.
Hi. Thanks for inviting us, Sam. So I'm going to talk today about how 3D Bitmojis are used in Snapchat and how we use them on AWS, utilizing all the AWS infrastructures and GPU to create these 3D Bitmojis. So I'm going to talk first about how exactly the avatars that we use today inside Snapchat were changed through the years, from going from 2D to 3D that we use today. I'm going to show how exactly we use those avatars inside the app. I'm going to discuss about how exactly the 3D architecture of creating these avatars and rendering them on the AWS works. And I'm going to give some specific examples how we actually use the AWS GPU instances, either the G4 or the G5dn that we currently use, both of them as a mixture. So Bitmoji started about 13 years ago. It started as creating some kind of comic strips for users. So you can see the one to the left. This is how it started. It was basically a 2D avatar that you created and then used them inside the web app to create kind of like comic strips that you can later share with your friend. When Bitmoji was acquired by Snapchat about 7 or 8 years ago, Snapchat decided to take this avatar and start integrating them into the app. We use them inside the app as kind of like identity for the user. So the user can use those emojis to kind of like represent themselves. They can customize the avatar to look the way they want, either like themselves. A lot of the user change the clothes on the avatar daily according to what they wear. So the original avatar that we started with, all up to the 3D one, were actually 2D avatars. They were just like vector graphics, SVGs graphics that we used to inside the app. They were also rendered in the cloud, but not using any GPUs, since this was just like a 2D. Although potentially you can, but there was no use case for that. Last year, we started developing the 3D avatar, the one you see to the right, and this is what currently users are experiencing in the app. The app today, of course, uses a mixture of 2D and 3D because this is kind of like an evolution. We can't introduce this at once because we have a lot of users, so we need to do like gradual introduction of the 3D Bitmojis. But this is how currently the 3D Bitmojis look in the app. So you can see it's a lot different than the 2D. This allows us to customize in very special ways how the avatar looks. Like 2D avatars are very hard to customize. The 2D graphics, you cannot rotate them. You cannot do any special like lighting effects, or animations are also very difficult. But when you have 3D, you have like complete freedom to change the avatar and animate them any way you want. So that's, I think, was one of the main reasons why we switched to 3D avatars. You can also see that the fidelity and the colors and the details on the avatar are much better than the 2D. So how exactly users are using those inside the app? The first one is in the profile page. This is the profile page of several Snapchat users. Once you create your avatar, you can put him as your profile, and this is how the profile is shared with your friends, either as a selfie or as a full avatar like you see here. So this is actually represents you. You can customize it and create it, and I'll show later exactly how you change that. And these are all like 3D images rendered on the cloud, and then like composed on top of some 2D background that you can also customize. Other location, people can use them inside the chat. So you can see the selfies. Once you create the avatar, we automatically create a selfie for you that you can also choose. We have around like 50 different selfies that you can choose. All of them are also 3D images rendered in the cloud. You can use it in the map, in Snapchat map. If you choose to share your location, other user will see your avatar. The avatar is also customized to show exactly what you're doing right now. So maybe if you're flying, we can automatically detect that you're flying, and we can show like you inside a plane. Or you can say, right now I'm like shopping, so the avatar will be shopping, or I'm driving, or maybe I'm in the rain or playing in the snow. Another one is when we use lenses. Lenses are kind of like interactive cameras that you can use to create effects. One of them is by placing your avatar, animated avatar, superimposed using augmented reality on top of the background. And it's also like fully 3D. You can rotate. If you change the camera, it will track the avatar and show you in different location. And lastly, we can also use them when you do the chat. You can choose stickers to send to your friend instead of just like along with other like chat sentences and words. You can also choose some stickers and emojis from libraries. We also create this library for you. So once you type some kind of a keyword, you will get this screen, and you can choose whatever sticker you want to send to your friends. So a couple of numbers. You can see here we have more than 360 million daily users. 250 of them are using Bitmoji dailies. We have over 1 billion avatars already created on the system. And you can do like almost like over 1 trillion possible outfit combination by changing all the aspects of the avatars. And right now, using AWS GPU instances, we render more than 1,700 million 3D images every day for the users. And this is why, by the way, this is not like the app is not like fully 3D. So for example, the experience for the editor today is still 2D. So you can see here, you go into the editor, you select whatever attribute you want your avatar to use, the color of your hair, the skin tone, whatever you're wearing. For example, now that we have FIFA World Cup, you can choose to wear your favorite team shirt or anything else, change the colors. So once the user like select whatever they want to wear, we go back to the GPU instances to actually create the 3D representation of the avatar, the 3D mesh. So first, we assemble all the parts that our creators created. This can be like pieces of the shirt, of the shoes, of the face, of the body. We assemble everything together. We build a 3D mesh. The 3D mesh is fully rigged, so it has a skeleton that you can later like use to animate the avatars, and also morph targets on the face that you can use to generate like facial animations. Also, we have base texture that were created to represent the avatar, like the face or everything. This is shared by all avatars, but since each avatar might have its own specific color tone, we need to recolor this texture, so we also use GPUs to do that for us. We assemble everything together, we export it as the GLTF, and we store it on Amazon S3. So like I said before, we have almost 1 billion of these already stored there. So everything that we do runs on EC2 GPUs using G4dn and G5 instances, and it takes about almost a second to assemble like all this together. and then cache it on S3. We want to cache it because later when we actually want to animate it, we don't want to recreate the avatar. It's a very expensive process. So once we have the avatar, and since, like I told you before, it has a skeleton, you can animate it and you don't have to recreate it unless, of course, the avatar change some of the attribute. This is how the avatar looks like using the, this is the vertices, like the wireframe view, and this is exactly how it looks like once you render it. These are the colors that we use to actually assemble inside the avatar. These are after, the texture you see here are after we went through the recoloring process. And then we assembled all of them together inside the GLTF, and you see this creates the avatar that you see on the right. So how do you do the rendering? So once we need to render something, to render a sticker or a profile page, we download these we download the animation and the models from S3. We upload all the model geometry and textures into the GPUs, and then we use a custom version of Filament Engine. This is a rendering engine created by Google. We use this engine to actually render it. We had to create some specific changes. Since this system is running in the cloud, it's headless. It doesn't have any windowing system. So we created some changes to make sure that the process is very efficient and also can work without any windowing system, headless completely on the cloud, on the instances. And this is how it looks like after you take the model and apply like serval animation to it. So this is everything you see here is the same 3D model, just like a different animation applied to it. The animation can either be like skeleton animation, which usually apply like to the body, to how you place your hands or your shoes or your feet. And for the facial animation, we use morph targets, which are also part of the animation as well. So how exactly all of this is actually architected? So once the user on the client like send a request, this will go to the Amazon Cloud CloudFront CDN. So this will actually load balance all the requests. We have a lot of them, so we need to make sure that we can actually spread this correctly among different GPU instances because we need to use a lot of them. We have a Kubernetes cluster that's running on EKS that actually handles those requests. Also allows us to scale up and down the cluster size because the usage statistic during the day can vary from lows and highs can be like almost 2 or 3 times. So we want to make sure that we optimize the usage and we don't use or deploy too many clusters or too many nodes when you don't actually need them. So we're running everything on hundreds of EC2 G4dn and G5 instances. These are like some mentioned NVIDIA T4 and A10Gs. And like I said, they can optimize. This is very important for us. Since these resources are very expensive, we want to make sure that we utilize everything according to actual usage, and we're not like over-provisioning or under-provisioning the number of nodes during the day. When we switched from G4dn to G5, we saw a very good performance improvement. So basically, I think latencies, which we measure like how long it takes actually to create and render everything, we're up by more than 30%. So give us like this helps us to improve the experience to the user. So definitely, we saw a huge gain there. Okay, I'm gonna show a demo. The app actually running this everything as I talked about, and I'll explain exactly what's happening. So this is a recorded demo, not live. So once you go into the app, you see a profile page. Again, this is a 3D images rendered on the cloud. You can go and customize it. So you open the editor. Like I said, it's in 2D today, but we're moving forward to 3D in the future. Customize the color of your hair, the shape of your hair, whatever you want to. Maybe you're wearing glasses. Other stuff you can do potentially is like maybe change the shape of your body, like from heavy body to light body. And once everything is done, let's see, we can do some other options. Yeah, maybe the skin tone or the color of the hair. Yeah, once this is done, we actually save that. And the moment you save that, this is sent to the cloud, and in real time, it sends you back the 3D images that you see here. So this is all happening in real time using the infrastructure on the cloud that I mentioned. You can also go and change like whatever you're wearing. So for example, this FIFA, like whatever soccer teams you're actually following, so you can change whatever t-shirt you want to wear, like Argentina or other teams. And again, whenever you change something and you save it, it goes back to the cloud instances, it recreates the avatar, the 3D avatars, it renders all these images, and it sends them back to you. So like different shoes, for example, if you recolor the shoes, and again, this is created in real time on the cloud instance. And you can customize the background. Here you can see all the images that were rendered. So once, because we want to make sure that the process is very efficient, so once we actually upload the avatar, at that moment, it's very efficient to render multiple images. So we take advantage of that, and once the avatar 3D model is on the cloud, it's inside the GPU, we render all these 3D selfies and all these profile images because it's very cheap at that point. We don't have to reload. Applying animation and rendering is fast, but uploading everything to the GPU is slow, so we want to take advantage of that. That'd be all. Next, I'll call Brian from Mircom to speak about their experience. Thank you.
Hello. Okay, my presentation is on optimized unified pane of glass for smart buildings on AWS. Agenda, who we are, where we were, our cloud journey, where we are today, and a short video. So who are we? We are headquartered in Toronto, proudly Canadian. In the spirit of the World Cup, I'm wearing a Canadian jersey. We are the largest fire alarm distributor and manufacturer in North America. All of our fire and life safety products are regulatory agency approved by underwriters laboratories, UL, ULC, and Factory Mutual, FM. This is my favorite slide. We are a family-owned, privately held company. We were founded in 1991 by Tony Falbo. Today, his 3 sons help him run the company. So from left to right, we have Mark, Tony, Rick, and Jason. Jason's actually here today. This is our vision statement: to make safer, smarter, more livable buildings. This graphic has changed over the last 10 years, and it's probably going to change over the next 10 years. The main thing is our vision will stay the same. The mission-critical building technologies we focus on are fire and life safety, automation, and security. Where we were. OpenGN was developed over 10 years ago as a centralized fire alarm system for monitoring single site fire alarm control panels. Single site monitoring our fire alarm control panels. As you can see here, it displays building experiences in 2D floor plans and 3D buildings in a single pane of glass. Okay. OpenGN's graphically intensive workloads require and mandate a dedicated graphics card. As a result, we have sourced a number of third-party on-premise hardware appliances in order to support our customers and accommodate our customers' various building experiences. Here we also support our fire alarm control panels and our building IoT fire sensors. When we take a deeper dive, we realize that our operational technology is very Windows-oriented. Windows operating system, desktop, database, and hardware appliances. Our cloud journey. Our customers are pushing our OpenGN's performance limits. Our largest on-premise hardware appliances can support 250 to 300 buildings. However, a lot of our customers require two to four times this requirement. In order to do this, we basically are working with AWS to modernize our platform. Basically, last year, 2001, we started to rehost our lift and shift OpenGN to Amazon's EC2 G4dn instance. The lift and shift was successful. However, the overall cost was higher than our on-premise hardware appliances. As a result, later last year, we decided to refactor and platform OpenGN to Amazon's EC2 G5G instance. We refactored from OpenGL1 to OpenGL3 ES, and we replatformed our operational technology to open source software. This is a roadmap. So basically, in Q1 this year, we refactored our custom-developed OpenGL1 rendering engine to OpenGL3 ES in order to support shader language. After this was completing successful in Q2, we replatformed to Ubuntu 18.04 and Mate Desktop and MySQL 8 based on AWS's recommendation. Currently, we are finalizing our minimum viable product, and we are planning to go to market via AWS's marketplace. Where are we today? Today, OpenGN is a digital twin IoT platform providing a cloud-based unified pane of glass for fire and life safety and other mission-critical building technologies. With the help of AWS, we're able to modernize OpenGN from a single site building experience to a multi-site cloud experience. Refactoring to OpenGL3 allows us to support multiple platforms: Windows, Linux, Mac OS, and WebAssembly. Finally, our OpenGN Gateway allows us to unify and integrate other mission-critical building technologies. Aside from our fire adapter, which supports our fire alarm control panels, we've built an automation adapter for Modbus, which allows us to integrate third-party fire alarm control panels and other building automation controllers. Finally, we have developed a wireless IoT adapter for Zigbee, which allows us to integrate third-party consumer IoT devices. Okay, quick video.
OpenGN is our digital twin and IoT platform providing a unified pane of glass for various building experiences. And now, with the help of AWS, we can support cost-effective cloud experiences, making buildings safer, smarter, and more livable. OpenGN was initially developed to make buildings safer. This is a fire control panel twin with an alarm event generated by a pull station activation. Here's an example of an access control twin with an alarm event generated by a door forced open. Here's the corresponding video twin of the alarm event generated by the door forced open. OpenGN not only makes buildings safer, but also enables buildings to be smarter. This is an HVAC twin of a rooftop unit sharing its IoT data. Here's an example of a utility twin for three-phase power metering. Other forms of sub-metering include gas and water. All this real-time IoT building data is captured and stored in a relational database management system and easily used for building analytics. Finally, OpenGN not only makes buildings safer and smarter, but more livable and sustainable. This is a thermostat twin for energy control. Here's an example of an occupancy twin for lighting control. And last but not least, here's an example of a phone twin for real-time audio-video communication. Open Graphic Navigator, enabling safer, smarter, and more livable buildings.
Thank you.